Mastering Sorting Algorithms, a deep dive into efficiency, complexity, and real-world applications in the ever-evolving world of computer science and software development. Sorting algorithms stand out as both foundational and transformative tools. These algorithms form the backbone of numerous applications, from simple list arrangements to sophisticated data analysis frameworks. Understanding their intricacies is essential for anyone striving to build optimized and scalable solutions. The journey into sorting algorithms reveals a fascinating blend of mathematical elegance and practical utility. Whether you're dealing with massive datasets or refining user experience interfaces, knowing which algorithm fits your needs can make the difference between a sluggish system and one that operates seamlessly. Let's explore the depths of sorting algorithms together. The fundamentals of sorting algorithms. Sorting algorithms are designed to rearrange collections of items according to specified rules. At their core, these algorithms manipulate data structures to achieve desired orderings, making them indispensable in fields ranging from databases to artificial intelligence. Their primary purpose is to transform unordered data into structured formats that facilitate faster searches, easier management, and improved analytics. The effectiveness of a sorting algorithm hinges on its ability to handle varying data sizes efficiently. While smaller datasets may tolerate slower algorithms, larger volumes demand high-performance methods capable of executing swiftly even under heavy loads. This distinction underscores the importance of selecting the appropriate algorithm tailored to the task at hand. Comparison-based methods. Many sorting algorithms rely on pairwise comparisons to determine element order. Examples include quicksort, merge sort, and heap sort, which leverage recursive partitioning or heap properties to achieve optimal results. Non-comparison techniques. Algorithms like radix sort and bucket sort operate outside traditional comparison paradigms, utilizing digit-wise sorting or distribution mechanisms to enhance performance for specific data types. Categorization of common sorting algorithms. To navigate the landscape of sorting algorithms effectively, categorizing them based on operational principles provides clarity. Comparison-based algorithms dominate many standard implementations, whereas non-comparison approaches offer distinct advantages in particular scenarios. Recognizing these categories aids in making informed decisions regarding algorithm selection. Among the most widely recognized sorting algorithms are bubble sort, insertion sort, selection sort, quicksort, merge sort, heap sort, shell sort, and TIM sort. Each has unique characteristics that influence its suitability for different applications. Exploring these variations equips practitioners with diverse options to address varied computational demands. Understanding time complexity. Time complexity serves as a critical metric for assessing algorithmic efficiency. Measured using Big O notation, it quantifies how execution time grows relative to input size. Efficient algorithms typically exhibit lower asymptotic growth rates, ensuring scalability across increasing data volumes. Analyzing typical time complexities reveals patterns among commonly used sorting methods. Quicksort generally performs optimally with an average case of O(n) log n, although its worst-case performance deteriorates to O(n) superscript 2. Conversely, merge sort maintains consistent O(n) log n behavior regardless of input configuration, albeit at the cost of higher memory consumption. Bubble sort demonstrates linear time complexity in best-case scenarios but degrades significantly to quadratic time in worst cases, rendering it unsuitable for large-scale data processing. Insertion sort follows similar behavior but often executes faster in practice due to minimal overhead associated with adjacent swaps. Selecting an algorithm with favorable time complexity ensures predictable performance outcomes. Developers must balance factors such as data volume, potential worst-case scenarios, and resource availability when determining suitable candidates for implementation. Evaluating space complexity. Space complexity refers to the amount of memory required by an algorithm during execution. In contrast to time complexity, this measure focuses on auxiliary storage requirements rather than raw computation duration. Assessing space usage is particularly important when optimizing for constrained environments or minimizing runtime overheads. Different sorting algorithms demonstrate varied memory footprints. In-place sorting techniques, such as heap sort and quicksort variants, minimize external memory allocations by manipulating original data structures directly. However, these methods sometimes sacrifice stability or increase risk exposure to worst-case behaviors. Merge sort necessitates additional temporary storage proportional to input size, resulting in increased overall space consumption compared to other alternatives. Nevertheless, this trade-off enables guaranteed O(n) log n performance irrespective of initial data organization. Choosing between these approaches depends heavily on project constraints and expected workload characteristics. Stability becomes another consideration when analyzing space complexity effects. Stable sorting preserves relative positions of equal elements, which is crucial for maintaining data integrity in applications involving linked records or hierarchical relationships. Choosing the right algorithm based on scenario contextual awareness plays a pivotal role in selecting optimal sorting algorithms. Various factors, including dataset size, available memory, presence of duplicate values, and pre-existing order, significantly impact algorithm efficacy. Evaluating these variables guides decision-making towards implementing effective solutions. Data size dictates algorithm applicability, with smaller inputs tolerating less efficient methods while larger volumes benefit from divide-and-conquer strategies offering logarithmic scaling. Memory limitations also impose restrictions. Algorithms consuming substantial auxiliary space become impractical in low memory settings. Prior knowledge of duplicate elements influences stability expectations. If preserving original sequences matters, opting for stable algorithms avoids disrupting relational data integrity unnecessarily. Similarly, recognizing partially sorted datasets allows leveraging adaptive algorithms designed specifically for exploiting existing orderings. Profiling actual system behavior through benchmark testing complements theoretical analyses. Empirical measurements reveal real-world performance nuances obscured by abstract computational models, enabling accurate predictions about algorithm behavior under target conditions. Practical implementation considerations. Translating theoretical knowledge into working implementations requires careful attention to implementation details. Language-specific features, library integrations, and platform constraints collectively shape viable deployment options. Considering these aspects enhances chances of successful integration and long-term maintenance viability. Modern programming languages often incorporate highly optimized built-in sort functions derived from decades of research advancements. Leveraging native implementations frequently yields superior performance compared to custom-coded equivalents, and less specialized requirements mandate bespoke modifications. Concurrency introduces new dimensions when designing multi-threaded sorting architectures. Ensuring thread safety while maximizing parallelism presents engineering challenges requiring synchronization primitives and strategic workload distribution schemes. Properly managed concurrent sorting improves throughput without compromising correctness guarantees. Safety concerns arise when handling sensitive information undergoing sorting operations. Implementers must ensure secure execution paths prevent unintended disclosure through side channels or improper access. Controls affecting intermediate states. Adhering to strict confidentiality protocols safeguards against potential vulnerabilities lurking within seemingly innocuous transformations. Real-world applications across industries. Sorting algorithms permeate countless industries, driving innovation through enhanced data manipulation capabilities. From enterprise-level applications to consumer-facing technologies, their influence extends far beyond academic study halls into everyday digital experiences. E-commerce platforms utilize sorting extensively to personalize shopping experiences dynamically. Product listings get ranked based on relevance scores calculated using machine learning models, ensuring users encounter curated selections aligned with browsing histories and preferences. Such intelligent curation relies fundamentally on robust underlying sorting infrastructures. Social networking services employ advanced sorting techniques to manage vast amounts of user-generated content. Feeds are organized using hybrid approaches combining chronological ordering with algorithmically determined importance weights, allowing personalized views reflecting individual interests accurately. Behind this seamless interaction lies complex algorithmic orchestration facilitating smooth navigation through endless streams of information. Financial institutions depend critically on precise temporal ordering for transaction verification processes. Time-stamped records undergo rigorous sorting procedures guaranteeing atomic consistency across distributed ledger networks. Maintaining exact sequence fidelity prevents fraud attempts exploiting race condition exploits inherent in improperly sequenced events. Scientific research benefits immensely from well-implemented sorting routines managing experimental datasets containing millions of observations. Statistical analysis workflows rely upon properly sorted distributions enabling accurate hypothesis testing and model validation efforts crucial for drawing reliable conclusions from empirical evidence. Emerging trends and future directions. The field of sorting algorithms continues evolving alongside technological progressions shaping modern computing landscapes. Emerging paradigms challenge conventional wisdom surrounding established methodologies, prompting re-evaluation of long-held assumptions about optimal practices. Quantum computing heralds revolutionary changes poised to redefine algorithm design fundamentals entirely. Quantum-inspired sorting proposals suggest novel ways harnessing superposition states for unprecedented acceleration gains previously thought unattainable using classical computing architectures alone. Early-stage experiments indicate promising avenues worth pursuing despite current implementation hurdles. Machine learning integration opens exciting possibilities for self-adaptive sorting mechanisms responsive to dynamic environmental shifts. Reinforcement learning agents trained through extensive simulation cycles develop emergent behaviors optimizing sorting efficiency automatically without explicit rule definitions provided upfront. This autonomous adaptation capability represents significant departure from static algorithm configurations traditionally relied upon. Blockchain technology fosters decentralized consensus mechanisms dependent on synchronized event sequencing maintained globally across peer-to-peer networks. Specialized cryptographic hashing combined with innovative proof-of-work constructions enable verifiable sorting assurances ensuring immutability and trustworthiness across geographically dispersed nodes operating independently yet cohesively. Edge computing initiatives emphasize localized processing reducing latency bottlenecks caused by centralized cloud infrastructure dependencies. Embedded devices equipped with microsorting engines execute lightweight operations autonomously, enhancing responsiveness while conserving bandwidth resources reserved for mission-critical communications only. Conclusion: mastering sorting algorithms empowers developers to tackle complex problems with confidence and precision. By understanding the nuances of various methods, considering real-world applications, and anticipating future trends, professionals can implement solutions that meet today's demands while remaining adaptable to tomorrow's innovations. As you continue exploring this vibrant domain, remember that continuous learning remains paramount. Engage actively with coding communities, experiment relentlessly with different implementations, and stay abreast of cutting-edge research breakthroughs reshaping our collective understanding of computational efficiencies continually advancing forward.